So so we have this path integral, right? And so this path integral involves integration over all configurations, and then there is a huge redundancy, right? There is a diffeomorphism while, and so the way how we can think about this integral is that this is a whole space. This is a whole space of configurations, and so there are two ways. So we have to integrate over all of them. So I'm just going to draw a line here, and so this is a gauge slice, right? So this is a gauge slice. A gauge slice, which means that if I start at this point, right? So if I do diffeomorphism transformation on my fields or while transformation, I will move to the left or to the right. Okay, so this is of course this multi-dimensional space, but I'm drawing this just as a line. So by saying that that's a gauge slice, it means that doing diffeomorphism or while transformation moves me along the slice. Okay. And so this type of changes, so of course, naively that will correspond to a different configuration that we have to include in the path integral. But they are not physical. They are related by gauge transformations. And so in fact, what we want to do, we want to make our integral, we want to integrate along the trajectories which are always perpendicular to this gauge slice. So we want to intersect. So this is integrating over trajectories. That intersect each gauge slice once. So if we do that, then in this path integral, so before the path integral was the integral over dx dg, right? Over volume of the diffeomorphism times volume of the y. So once we integrate along the directions which are normal to this gauge slicing, so then we integrate over just the physical degrees of freedom dx, right? So we kind of evaluated the dividing part in the path integral by the diffeomorphism and while transformation. Of course, what we would have to do, so that's the idea for gauge fixing. So our gauge degrees of freedom are diffeomorphism and while transformations. And fixing gauge degrees of freedom, so I'm canceling these volumes in the denominator. So is it clear what I said?
Here I have another question.
Right.
When we do the ordinary quantum field theory, it seems we do not care about the diffeomorphism invariant, although the field theory always.
Right, because you formulate your quantum field theory in flex space. Right. So now, what am I? Okay, so you guys don't have questions, and I do have a question. So what am I implicitly saying here? Okay, I told you that once I do that, then I am canceling the denominator. When is this correct? Sorry? I'm asking a question. So I was telling this picture is a gauge fixing, and I was saying that once I integrate, so I choose a particular point, and then on each gauge slice I choose a particular point, and I integrate along the trajectories, intersects each gauge slice once. And I'm saying that corresponds to dividing, to writing, just omitting the denominator. What am I assuming here? I'm assuming the counting string. Sorry? So I'm change the variables to open. Well, we'll handle with that. Yes, there will be a gauge fixing, but I'm saying there is something that I'm. So if you, what you are missing right now, you're missing the fact that the string theory will only live in 46 dimensions, so in critical dimension. But this is a place. This is a place where, which will separate whether you're missing or not. What's implicit assumption here, right? So when I'm saying that that's the case, I'm saying that this trajectory and this trajectory is the same, right? So if I choose a trajectory that slides, each gauge slides in this way or in some other place, so I can go from one to another by doing a diffeomorphism Weyl transformation. All I'm saying by doing that I will get the same answer times a constant, and that's why I have been able to cancel this constant in the denominator. So what I have been assuming here is that an integration of a different physical trajectory, I will call it a physical trajectory, produces the same answer. In other words, the assumption here is that diffeomorphism plus Weyl symmetry is exact quantum mechanical. Okay? So we're talking about exact. What we will find out is that in general, there will be anomalies in this. So we know that these symmetries are classically correct, right? Because the action there is invariant under diffeomorphism and Weyl symmetries. But this is inside the path integral, which includes all quantum corrections. And so, this in quantum field series, this can happen. This can happen that your gauge symmetries become anomalous. And if that happens, you're usually in a bad shape, usually very, very bad shape. You either violate unitarity or something really bad happens. So you never want to have anomalous gauge symmetry. And so it will turn out that in particular, when we require, okay, so the first thing is that we will find out that in order to have, okay, this is what I'm not going to show, but I'm just going to mention here, that if you want diffeomorphism invariance to be anomaly-free, remember that we looked at central charges of the CFTs that can have different central charges. It turns out that unless the central charges are the same in a holomorphic and anti-holomorphic set, the diffeomorphism invariance is broken. Okay? And unless the total central charge is 0, the Weyl symmetry is broken. Which means that everything that we're going to do now, right, and what we are going to do, we're going to fix a metric to this particular form, and where we can do that only if this symmetry is exact quantum mechanically. Okay? So everything that we do from now will be wrong unless, at the end of the day, the total central charge of the theory will be equal to 0. Because see, once I write it down in this way, then I'm dealing with a conformal theory for this X system, right? So that's a conformal CFT, and so I'm asking the question: what's the central charge of that? So the issue here, somebody already mentioned that there are Fourier-Popov determinants. That's what we're going to discuss. So we'll find out that there is a contribution to the central charge of the CFT in this conformal gauge coming from this Fourier-Popov determinant. And so here, the condition that these symmetries are exact quantum mechanically will actually lead us to the critical dimension of the string. Okay? Good. So let's go ahead, and so we will worry later about this, and we will study later how does anomaly arise if we move along the gauge slice. But for now, so let's fix, we're sitting in this gauge fixed slice, which means that delta, our metric, GAE is GAE hat, which is delta.
Alex, can I ask, we don't have any problems calculating semi-classical approximation, so like several approximation, in calculating this.
Yes. Yes, so this is a path integral perspective. But in quantum field series, anomalies arises at one level. So in fact, in particular, when we talk about chiral anomalies in gauge series, so those are kind of similar things. that there is a symmetry that's exact classically, but it's anomalous once you include quantum corrections. So if you take a quantum field series, then anomalies typically arise at one loop level. And moreover, and so in, say, chiral anomalies, as I mentioned, the violation of the symmetry, how the symmetry is violated, is just completely determined by one loop result. So it can also be shown. Meaning that further correction to the violation from higher loops doesn't show up. Okay. Right. Of course, I'm assuming that you guys already passed quantum field theory 2, which I know some of you are just taking. But that's kind of fun thing that you see there. Okay, so very good. So so now we have to go ahead and compute the path integral along this physical trajectory. And so the first thing we need to discuss are the Faddeev-Popov determinants, right? Faddeev-Popov determinants. And so in general, so let's describe mathematically the type of gauge symmetries that I'm doing. So this psi, so this moving left to the right is acting with psi. And so this psi is a transformation when I start with symmetric GAD. And so it goes to GAD psi as a function of sigma prime. And so this equals e to the 2 omega of sigma. So this psi involves Weyl transformation, and it involves the diffeomorphisms. So del sigma, sigma c over del sigma prime a, del sigma d over del sigma prime d, right? And so here I have g c. Okay, so this is a general gauge symmetry moving along the slides. So this is diffeo, and this is y. And so as a gauge series, it's helpful if you've seen this before, but if not, I'll try to be consistent. But please ask me questions. There will be questions. So we're going to introduce a Faddeev-Popov measure. Introduce Faddeev-Popov measure. Okay, and I'm going to introduce it in such way. So 1 equals this Faddeev-Popov measure. So it will depend on fiducial metric. By fiducial metric, I mean this gauge fixed metric. Okay, you can think of this as gauge fixed metric. And so here is an integral inside delta function g minus g psi. Okay. So so what I mean here is the following fact, right? So you know that if I have an integral dx and I have delta function of x minus say x naught, so this equals to 1. But in general, if I have an integral of dx and here I have a delta function, say f of x minus f of x naught, right? So this integral, so this is an integral of a delta function. So this integral is not equal to 1, but this integral is equal to what? 1 over f prime of x naught, right? So you can see it that on this one-dimensional example, I have 1 here, and I have f prime of x naught, right? So this is my Faddeev-Popov determinant in this one-dimensional example, right? And the reason it arises because when I introduce delta function, I introduce a delta function which depends in a functional way on the parameter over which I integrate. So the story is exactly the same here. So here I have parameters of my symmetry group, right? But I integrate with respect to metric that depends on this transformation parameters, right? So this is very much like the situation here. So the meaning of this Faddeev-Popov measure is exactly this additional piece that is necessary to go. So for example, if I would have here an integral of dg of delta function of g minus g dg data, then this integral would be equal to 1, which is exactly the same that if here I would integrate df of x, right, delta function of f minus f of 0. So this integral up here would also be 1. So the non-trivial fact of the Faddeev-Popov determinant comes because we integrate over h degrees of freedom, and but what depends here on the gauge degree of freedom of metrics. So these are non-trivial functional, and it depends in the way how I describe it. That's the one above. Okay, so we're going to make the following two assumptions that can be justified, but I'm not going to do this justification here. So the first assumption, so we assume that the measure is gauge invariant. Okay, so there is a way of introducing a gauge invariant measure on a symmetry group space, right? So that's always possible. So we assume that this measure is gauge invariant. And the second assumption that we're going to make is that the delta function is gauge invariant. We assume that delta function is gauge invariant. And so that's kind of obvious thing, right? So the delta function integrated. So if I have this integral delta function of psi minus psi naught equals to 1, so that's how we define a functional delta function. So if we're going to say that the measure is invariant, okay, 1 is a number, it's invariant, then the delta function must be invariant. So let's say this. A simple statement, but we still have to assume it. Okay. So given that, we can prove that. So given these two things, we can show that the Faddeev-Popov determinant is actually gauge invariant. Okay. So the Faddeev-Popov determinant, when I evaluate at G, so this is my metric G sitting at this point here, and then I can act with psi. So here I will get the metric G psi. And so the Faddeev-Popov determinant is actually unchanged. So the Faddeev-Popov determinant evaluated at G and G psi, which is obtained as they move along the gauge slice, will not change. So let's prove this statement. So by definition, what we mean by this Faddeev-Popov, Faddeev-Popov of G psi is a -1. So I'm just moving this guy on the left. So this equals to the integral d psi prime, delta function of d psi minus g psi prime. So what I'm doing, so this delta function measures the difference between two metrics on the gauge slice. And so what I can do, right? So I can move, I can act on this with a gauge transformation and use the fact that delta function is gauge invariant. So, so what I'm saying is that, let me draw you a cartoon picture here. So this is our gauge slice. So this is psi. This is psi prime. And so what I can do, I can act with gauge transformations and compute the difference by moving this guy to the identity. Okay, so I move this guy. I want to move this guy along the gauge slice to identity, which means that I act on this with psi to the -1 transformation. But then once this guy moves to the identity, right, and this I will make field circle. So if this guy moves to 1, then this guy will move to psi minus 1 psi prime. Okay? So I have to act with the same symmetric transformation on both g psi and g psi prime. So then my integral becomes a delta function. So identity tells me that I have bathymetric g, and then here I have minus g psi minus 1 psi prime. Okay. Now what I can do, I can just simply change the variables of integration. I'm going to call this guy psi w prime. Okay. So what I did, I just shifted integration along the H slice. Instead of integrating with respect to psi prime, I'm integrating psi minus 1 times psi prime. And so this, using the invariance of the measure, I can write this down in this form, delta g minus g psi delta. But this is precisely what we call Fourier-Popov determinant for the metric G. Okay, so we demonstrated that a Fourier-Popov determinant is invariant. Okay, so very good. So now we're going to do exactly the same steps as people do when they talk about H series. So we're going to insert this Fourier-Popov determinant inside the path integral. Good. So so I'm going to write down my path integral to have an explicit dependence on this g hat. Okay. So the g hat is this. So this was our physical slice. And the metric here is g hat. Right? So that's a fiducian metric. So I'm writing down this explicit dependent. The reason why we want to keep this explicit dependent because later we want to remember we want to look for anomalies in the symmetries. So we would like to move from one g hat to another one and see if the position function stays the same. Here, so we keep explicit dependence on position. Okay, that can now. Explicit dependence on the distribution metric. And so what I did is the following. So before we had this integral dg, so volume of the homomorphism times volume of the y. And then I have e to the minus s. Which was dependent on x and g. So we did analogiate x and g. So that's the original Polyakov path integral. And so what I did, I multiplied it by 1. Okay? But I multiplied it by 1, which is this path integral. Okay? So that's the 1 that I'm going to write down there, times 1. And this one is going to be Fourier-Popov determinant as a function of g, and then I have a delta function of g minus g psi, and I have one additional integration here with respect to g psi. Okay, so is that clear? So very good. So, so I told you that the problem with this Fourier-Popov determinant arises because we integrate metric with respect to del psi, but this integral is very simple. Okay. If I integrate with respect to GG, then what I'm going to get, I'm just going to get, I'm going to get 1. So I can explicitly compute this integral first. And so I will be left with the integral of d psi, and then I have dx. And I have to divide by the differential across phi. And then I have delta Fourier-Popov. So now once I integrate with respect to delta function, whenever I see g, I have to substitute this argument of the delta function. So it's going to be g hat of psi, right? So this is our fiducial metric. And then I have e to the minus s, that depends on x, and g hat of psi. So, good. So now the next step to do is to say that, so x, the matter itself dx does not depend on these transformations, right? So our field was our field x was a scalar, and moreover, this guy is invariant on the psi transformation. So I can remove psi from here. It doesn't depend on psi. So there is no dependence on psi. No dependence on psi. No dependence on psi. No dependence on psi. And the action itself is invariant, right? So it doesn't depend on psi. So I can remove. Okay, so you can see that in this path integral, nothing depends on psi, so the only dependence on psi comes from here. But the integral with respect to d psi must be exactly the volume of symmetry transformation. So this integral here will cancel exactly what I have in the denominator, and so we will have an integral of dx. And then Fourier-Popov determinant of g psi, and then I have e to the minus s x dx. Okay? So again, the point is that we started writing down the path integral for a single string, and it has a lot of symmetries. And then we said that we want to evaluate only along the gauge non-invariant or along the orbit, which is not a redundancy, and so restricting to the fact that our integration trajectory intersects each gauge orbit once, reduced for us this Fourier-Popov determinant. And in doing so, we remove this denominator. Very good. So, if you have any question, now is the time to ask about the steps that we have done so far. Good. So our next step is that we want to evaluate this Fourier-Popov. Okay. So we want to compute of g hat. Okay, so for now it depends on g hat. I didn't say anything what this g hat is, but
So, can I ask you a
Yep.
question? Why the action cannot depend on the site?
Because it's invariant, this is a classical action, and it's invariant under diffeomorphism and Wild transformation. That's why it doesn't depend on time.
But if you do the diffeomorphism transformation, you should change in the scatter field.
Yeah, I have to change from sigma coordinate to sigma prime, but the action will look exactly the same way. So the integral over d sigma will be exactly the same as the integral with respect to sigma prime. Right, so the classical, what enters in the past integral is a classical action, and that was invariant under diffeomorphism. So the only, you can see that the only problem and the only subtleties can come up only from the mesh of integration. And so this gauge fixing produced for us is Fadeev-Popov determinant. That's just a simple additional piece. Okay, so very good. So let's go back. And recall our definition of the Fadeev-Popov determinant, right? So delta Fadeev-Popov. Delta Fadeev-Popov minus 1 function of the fiducial metric equals to an integral of d psi. And here I have delta g minus g psi. Okay, so the delta function will pick up So the delta function will pick up the values. I think I'm getting lost with where I have. I don't have to keep tab. Fine, let me do. So the delta function will pick up the values of psi such that gf equals to g hat psi. Right? So in general, if we have a complete gauge fixing, then there is a unique solution to this, right? So if I have a complete gauge fixing so that my trajectory indeed intersects only once, which means that this identity implies that psi equals to 1. Right? So out of this huge group of diffeomorphism and Wild transformation, it's only the identity for which that thing holds true. So we're going to assume that that's the case, even though that we know that there is a measured zero left over. But let's just proceed. Assuming that we fixed it. And so now, what I want to do, I want to ask the question: how does my metric transform under infinitesimal transformations, right? So when sigma is very close, when this psi is very close to the identity element. So for psi near identity, so we have sigma prime A. So this we must have infinitesimal diffeomorphisms and Wild transformations. So sigma prime A equals sigma A plus delta sigma A, right? So there is an infinitesimal transformation of my coordinates, and then there is an infinitesimal transformation of my Wild parameter. So normally we're going to fix conformal gauge, right? So we're going to choose delta A metric being just a flat metric. So we start with a Wild factor, which is 1, and so that changes to delta omega, okay? And so I'm saying that those are the changes due to moving slightly from the identity along the gauge slice, okay? So what I want to do, I want to know how does my metric change? How does my metric change if I make this change of variable? And unfortunately, I think I deleted. Remember, there was a general transformation, right? So GAB was going to G prime AB, which is e to the 2 omega, right? And then here there was del sigma over del sigma prime, del sigma over del sigma prime times G, right? I'm not writing down the indices. So that was the way how the metric transform in general are their arbitrary psi transformations. But now what I have to do, I'm going to ask how does my metric transform if I do linearized transformation. So I'm very close to the identity. The reason why I can do close to the identity because delta function only cares how does the argument of it vanishes, right? So it's exactly the same when we talked about the delta function of dx f of x minus f of x 0, right? So that delta function didn't care how does the function look like away from x naught. It only cared how does that function behave near x naught to leading order, right? And that's exactly what we're doing. That's why even though you might think first, look, you're doing just on the leading order, so you are not doing it exactly, but I claim that we do it exactly because of the delta function that eventually rules takes this result. So the metric transformation, so there will be corrections that come from changing this and come from here. So if you do the arithmetic, what you will find out that it's 2 times delta omega GAB, right? So this is an obvious fact, right? So you have exponential, and so omega changed by 1 plus delta omega, so there will be a change 2 times delta omega GAB. And then there are transformations coming from infinitesimal transformations there. And so that equals to minus nabla. I'm just going to write down the formula and refer to our favorite textbook. Okay, so this is the way how the method will transform under infinitesimal diffeomorphism transformations. So here I mean a covariant derivative. So if I have nabla A acted on a vector with a lower index BB, so this is del A BB minus Christopher connection C A B B C, right? And the Christopher connection gamma C A B is 1/2 G C K, and then here I have del A G DK plus del B GAK minus del K GAB. Okay? Again, this is simple to derive. You just have to do this infinitesimal transformation and expand it to the order, and this is what you And so I can write it down one more. Write down one more line here. Just doing an algebra. So I can write this down as 2 delta omega minus nabla C delta sigma C delta times GAB. Okay. So right. So you can see there will be a piece. Well, if you do all the algebra, you will find out that that's the case. And then there is minus 2. I'm going to write it down P1 delta sigma times AB. So what I introduced here, P1 delta sigma of AB is going to be equal to 1/2 nabla A delta sigma B plus nabla B delta sigma A and minus GAB. Okay. So what I did, I just took what I had here and I decomposed it, right, into a traceless part. So this is a symmetric traceless part, and I extracted the trace. Okay. And in doing so, I introduced I introduce this very neat operator, Q1. So this is a differential operator that maps covariant vectors into two forms, right? So it maps it into an object with a lower index into an object with two lower indices. Okay, very good. So so now we can go ahead and evaluate this delta function. Okay. So this idea for determinant is a minus one of the differential metric is going to be equal to the integral, right? So now I can write explicitly the measure of integration. So I have to integrate over all wild parameters, d omega, right? And I also have to integrate over d delta omega and d delta sigma. So those are the sort of local coordinates that specify moving along the gauge slice. And then here I have a delta function of the difference between the metric, and the difference between the metric is going to be minus delta GAD. Okay. So in other words, the inverse of determinant is d delta omega d delta sigma. And then I have delta function of minus 2 delta omega minus nabla c delta sigma c g a d. And finally, I have plus 2p1. Okay, I'm not going to write down the indices here. Plus 2p1 delta sigma. Okay, so any questions so far? Yeah.
I really don't understand what you mean by d delta sigma. It's integrating over delta sigma.
All possible functions. So think of that I choose some complete set of functions, and I write down delta sigma. Think about Fourier expansion. And so I write delta omega as a Fourier expansion over. So this integral will become an infinite dimensional integral over Fourier coefficients. You know where we talked about the kind of single thing when we talked about Schrödinger wave function, right? So we have to integrate over all possible values of x that's about it, right? So that was a functional integral. But what we did there, we expanded into Fourier modes. And we said that integrating over all possible x's at the boundary is the same as integrating over the coefficients of the Fourier modes.
Yes, but this is delta sigma, not sigma.
And that's enough, right? Because this delta sigma, so we have to integrate, over right, so I guess, okay, so I guess you are saying that there is an integral over the gauge slice, right? And I'm saying that there are, it was a little bit misleading. I was writing it as a one-dimensional thing. But in this, not sigma, Xi, in this Xi transformation, I can easily do this, okay? So this is an example of Xi transformation. I do a transformation at which I just do infinitesimal change of coordinates. So that's an example of Xi. And then another example of Xi is just to change omega into delta omega. Okay. So those guys, they are like constant values, right? So they correspond to identity. And so integrating over all Xi correspond to three integrals, right? There are three independent functions. This goes back to the counting that we did before. How many degrees of freedom? How many degrees of freedom we have? We have 2 reparameterization and 1 y, which means that there must be 3 functional integrals. So these are 2 functional integrals. I can do arbitrary delta sigma a, delta sigma 1, delta sigma 2, that's 2, and there is 1, 1. So here, what I have here is what I was denoting before as as DXR. Okay. Now I have been explicit, and there is no constraint between them. Okay. So in general, I can do these transformations independently. So the issues of the constraints, will lead us to this mismatch, which is measure 0. Right? I'm doing now generic transformation. Okay. So this single slice, right, when I was writing down the gauge slice as a line, is a manifold itself. And in that manifold, there is a particular line that corresponds to conformal plus Weyl transformation. But I'm not staying there. I look at the generic one. Okay. And that generic one corresponds to 3 functional integrals. Okay, so very good. All right, guys. So now I have to do time management because I don't want to stop at a stupid place, which would imply I have to redo everything next time. So let's go ahead. So I'm going to write down this in better form, and then we'll stop a little bit. So we have to continue massaging this integral, and so let me go into some aside, and remind you something. So again, let's look at the simple delta function, right? So delta function of a simple variable. So one way that you learned in your undergraduate math class is that the delta function of x, right, is an integral over d beta e to the 2 pi I beta x. So this is a Fourier integral representation of a delta function. You are familiar with that, I'm assuming, right? And here I'm writing down proportionality. It depends how you normalize your Fourier coefficients. Is it 1 over 2 pi, 1 over root 2 pi? It doesn't matter. So it's up to a constant. It's given by this integral. So if I have that, you might imagine that I should be able, there is an analog of this one-dimensional formula into a functional formula. And so it tells me that I can write down this delta function as one additional integral involving beta. Okay, so this is what I'm going to do. I'm just going to write down this Fourier-Popoff determinant. So I'm just extending this equality sign over here. So I have an integral with respect to d delta omega. There is d delta sigma. There is d delta sigma. And now I'm going to integrate. I'm going to integrate with respect to this additional beta, right? So beta, d beta. And so what this tells me, wherever you have the delta function, take the argument of the delta function and substitute it e to the 2 pi I beta times that. That's what it instructs me to do. And this is exactly what I'm going to do. So it's going to be e to the 2 pi I, right? Now this is a functional integral, right? So I'm just going to write it down. So this is going to be beta AB. Right? And so this is the analog of the x. Whatever is inside, this is the analog of x in this formula. So now you can see why I needed two indices, a and b. Right? The reason I needed two indices is because the combination inside here has indices a and b. Right? So what I will have here, beta a b, and then I have minus 2 delta omega minus nabla delta sigma times g plus 2 u1 delta sigma with lower indices a and b. Okay, so that would be if I had just numbers, but actually those guys, they depend on the world sheet. And so what I would have to do, I would have to integrate over a world sheet, so there will be an integral, and I have to integrate with a d-Fourier measure, so there will be an integral d to sigma square root of G. Okay? So what I'm claiming is that this step to go from a delta function to the exponential representation is given up here. Okay? Are you with me, guys? Good. So next step is we're going to look at this integral. Okay, so I'm just going to look at this integral up here. And so the reason I'm going to look because delta omega enters in a very simple manner. And so let me integrate with respect to del omega. Right? Notice that I have 2 pi I, so now I'm going backwards, right? So now I'm trying to go from exponential form into a delta function form, right? So if I integrate with respect to del omega, so I can see that I have 2 pi I, right? And so then I integrate with respect to beta, I have to, I will get a delta function of x, right? So if I integrate with respect to del omega, I will get a delta function of what? Beta AB, right? Beta AB times GAB, right? The reason is that this delta omega is multiplied by GAB. So I will get, after I integrate with respect to del omega, I will get this condition. So, so what is it clear? So minus 2 will simply mean that I will have a minus 2 here. It's, in principle, you have to worry, but you don't worry about constants. The constants in front of the delta function is minus 1 over constant. The important thing here is that further integration will restrict me when the argument of this delta function is 0, right? So this would imply that beta AB, this additional function beta AB that I introduced, must be such. So we know that it must be symmetric because GAB was symmetric, but actually what we are finding now is that it's also traceless. Okay? Because if I do the integral with respect to delta omega first, I will get a delta function of the trace, and it must vanish, which implies that I must restrict to a traceless beta AB. There must be traceless. So is there any question? This is an important first step. No. So once you realize that it is traceless, so this is a constant, but I mean this is some complicated function, but it doesn't carry any indices, right? So what you have this guy times GAB. Since you have to integrate over beta, which are traceless, then this guy vanishes. See, I looked only at the integral with respect to del omega, but it allowed me to kill both terms. Okay, so it allowed me to kill the trace part completely of this beta AB. So I can write this down. So this path integral, which is a Fourier for determinant, I can write down the final expression. And that would be a good place to stop. So I'm just going to write it down as an integral of d del sigma and d beta. Right. So remember that we integrated with respect to del omega, right? And so this guy, the way I put the prime here, I put the prime. So this beta prime AB equals to beta prime BA. So it's a symmetric function, and it's a traceless. Beta prime AA equals to 0. And so out of that integral, I will have what's left, e to the, so there is 2 pi I, and there is additional 2. So there are some places where 2's are actually very important. Otherwise, we'll screw up the critical dimension of the string. So here we have to keep track. So we have 4 pi I, right? And then I have an integral of D2 sigma, and then there is beta, beta prime AE, and then I have this differential operator, which I call P1 hat. Well, when I put a hat, I mean that it's evaluated with respect to a specific metric, right? So this P1 involved covariant derivatives, right? This is where we define it. And so I can evaluate it around any specific fiducial metric, and so that's what I mean by putting a hat here. And then delta sigma AB. And so what we computed, we showed that our Faddeev-Popov determinant as a function of a fiducial metric is given by that. And the one important thing that I'm missing is that we actually did not compute the Faddeev-Popov determinant, but we computed the inverse. Okay? And we showed that the inverse of the Faddeev-Popov determinant is given by that nice functional integral. So the next step, we're going to stop now, but I'm going to ask you, are there any questions so far? So what is important, remember that what we need in evaluating Kolякov path integral, in a Kolякov path integral, let me end up so that you will see exactly where we're heading and what the next steps that should be done. Remember that what we are doing, we're integrating, we reduce the Kolякov integral into this form. Right? So you can see where the problem is. Right? The problem is that, yeah, sure, we found a nice integral representation of the Faddeev-Popov determinant, but not quite. Right? So what Kent is in a Kolякov path integral is not the inverse of a Faddeev-Popov determinant, but the Faddeev-Popov determinant itself. And we cannot simply plug in 1 divided by z, because we have to compute a path integral with 1 divided by a functional limit. So what we end up doing is that so far those guys are all normal Bosonian fields, and next time we will start with a crash course on Grassmann variables, and we're going to rewrite this integral in terms of the fermionic coordinates. So I will explain you what I mean by fermionic integrals. And then from here, we will be able to represent not the inverse of the Faddeev-Popov determinant, but the Faddeev-Popov determinant plus 1 as some nice functional integral. And once we do that, we will be able to substitute it in the general formula. And that will produce for us, okay, so there will be an integral of something, e to the minus s gross, right? We will write down, after we go to fermionic coordinates, the Faddeev-Popov determinant as the action for the ghost field. And so the bottom line will be that a Kolякov action will be the action for the x field and the action for the ghost. And when we talk about conformal invariance, when we will require conformal invariance, we will need to require a conformal invariance of the total action. Okay, so but that's next time. Right, guys? So see you next week.